Good morning to all. So, any questions from last lecture? Okay, so let's start our lecture. So, in last lecture, we were looking at the operations we can perform on the singly linked list. So, in this uh, operations on the singly linked list, we are looking at, and in that we covered in last lecture the insertion operation and the deletion operation of a particular node whose address is given to us. Right? But I also told you can develop the algorithm for the value of some node is given to us, and that node we can delete. So when we have a value instead of address of node, at that time we need to see whether there are multiple copies of that value or not. So uh, it depends on the purpose and application. If you want to remove the first encountered node with the given value, or you want to delete all the nodes having the given value. So based on that, you have to write the algorithm. So uh, next, let's go ahead to see the operations on singly linked list. In that we have seen this insert operation, right? And we also have seen the insert at end operation, then insertion in the order, and we also covered yesterday delete operation. Okay, now next is the copy operation that I think where we stopped in last lecture. Am I correct? So for this copy operation, let's understand the steps of algorithm first. So this is a general algorithm to copy a linked list. So when you want to copy a linked list, you will copy one linked list to another, and for that the first step is, if the list is empty, then return null, and also you check if the availability stack is empty, then also you have to write the underflow. Why we do this? Because when you want to copy a linked list to another linked list, so in another linked list we need the number of nodes equivalent to the linked list which we want to copy. So to get these new nodes, we will require availability stack, and if there are no nodes available in this availability stack, then we have to declare that availability stack is underflow and we cannot go ahead. Okay. Or else, if there are nodes in the availability stack, then copy the first node, and you repeat through step 5 while the end of the old list has not been reached. Right? So until the end of the list, you have to repeat the step 4 and 5. So in the 4, what you have to do, you obtain the next node in the old list, records its predecessor node, and in the fifth, if the availability stack is empty, then say underflow. Otherwise, copy the node and add it to the rear of the new list. right? So here there are two terminologies used. One is a new list and another is a old list, right? The old list is the list which we want to copy into the new list. So in the new list, you have to copy this old list from the rear and set link of the last node in the new list to null and return. So this is a very simple procedure. So let's see the algorithm itself. So this is the algorithm for uh, so in this algorithm, here it is given copy and only first. Now what is this first? So this first is a pointer to the first node. It is a pointer to the first node in the linked list and and this function makes a copy of this list. And a typical node in the given list is having the info and link fields that we already know. Every node has these two parts. And the new list is to contain nodes whose information and pointer fields are denoted by field and PTR. See here they have taken two more variables like field and PTR, right? Because there are two lists, that's why. So the new list is to contain the nodes whose information and pointer fields are denoted by field and PTR. And the given list is consist of the node of the given list is denoted by info and link. Uh, Practically they both are same. So info and field are the same, only we are denoting it info and field, two different names. And link and PTR are also the same, having the same meaning. We are just using two different names, link and PTR. And the address of the first node is in the newly created list. The address of the first node in the newly created list is to place in begin. See now here the linked list is pointed by begin. So up to now we were pointing it to first. Now for this copy operation we will return the newly generated linked list with begin. And new save and predecessor are the pred. New save and pred are the pointer variables, right? They are a temporary variables, you can say. So clear with this description. So let's go ahead with the algorithm. So in this algorithm, the first task is if the first is equal to null, then return null, right? So there is nothing to be copied. Otherwise, you copy the first node, you check if availability stack is equal to null, then write underflow. Otherwise, use a new pointer to point to the node which is to be copied. So we will get this node. Getting the node from the availability stack is the same as the previous algorithms. Say new equal to avel. This new is now pointing to the node where avel is pointing. Now update the avel pointer. Avel equal to link of avel. Right? And the field of new is equal to the info of first. Right? And begin equal to new. So here you can see we are just copy the first node and we are given the linked list. Say let me draw here. let me take 3 nodes. Last node is pointing to null and all other nodes are pointing to each other, and this is the node which is pointed by the say first. Instead of first I just write n. So this is my linked list, and say there are contents x and y and z. So this is the list I want to copy, right? And for that I will get the node from the availability stack and it will be pointed by the new. So let me take one node here. And this is pointed by new. Instead of new I just write n. Okay. So now new is a node which I have got from the availability stack. Here I assign the field of new equal to info of first. So this is a field of new, right? And is equal to the info of first. So here x will be stored because the info of first is equal to x. And begin equal to new. So now I am creating a begin pointer and initializing it with the new. So instead of begin I write just b, right? Now initialize the traversal. For that you take one temporary variables pointer variable save, and it is pointing to the same node where first is pointing. So here instead of save I just write s. So s is now pointing to the first node. Now move to the next node if not at the end of list. So we have to repeat the steps till we have link of save equal to null. Right? So what we have to do? We have to maintain one more pointer predecessor. Right? So predecessor is equal to new. So here one more node, say one more pointer predecessor, that is p, is maintained, and save equal to link of save. So now after this step my save will be pointing to this, and this previously it was pointing to the first, but now after using this save equal to link of save it will be advanced to the next node. It will be pointing to the next node in the list. Now what you have to do, if avail equal to null, now you have to follow this taking the nodes from availability stack and creating a list which is pointed by the begin. Right? If it is null, availability stack is null, then say underflow. Otherwise the same procedure. Take a new node, right? So now take a new. So now new is pointing to this node. Okay. And avail equal to link of avail. This is for availability stack. Then field of new is equal to info of save. See, the field of new is equal to information of save. So information of save right now is y. So y will be copied here, right? And pointer of predecessor is equal to new. So this is predecessor. So pointer of predecessor is equal to new. Right? And then you have to go to check whether we are at the end of the list. So link of save is equal to null. No. right now link of save is pointing to some other node. So we again will follow these steps. So now again predecessor is equal to new. So this predecessor will be pointing to this new. And now this link will be overwritten. Okay. And the next step is save equal to link of save. So I am uh, advancing this save equal to link of save. So it would be pointing to now this node, right? So let me delete the link which is overwritten. Now save is pointing to this node. And what we need to do now, if we have to check again if availability stack is availability stack has nodes, right? If there are no nodes, that means avail pointer equal to null. So display it is underflow and return from the algorithm. Otherwise, take a new node. So let me take new node here. Okay, and uh, a new node is I have got from the availability stack, and the field of new is equal to info of save. So the field of save is now it is Z, which has to be copied to this, right? So let me copy it here. So that is Z, and the pointer of predecessor is to new, right? Actually, I forgot to update this link, and here when I say new equal to avail, that means this new is now pointing to the new node, right? And this link is to be over. So now pointer of predecessor is now new. So the pointer of this predecessor, this is a predecessor node. The pointer predecessor is equal to new. So it will be pointing to this new. And let's go to the again fourth step to check whether the link of save is equal to null. Yes, it is null. Right. So this condition is broken, and we will come to the seventh step. And here at the seventh step, pointer of new equal to null. So pointer of new will be set to null and return the begin. So this begin has to be written. Now this begin is the new linked list. This is the exact copy of this first. Right? Any questions from this? Have you got this? Roll number 7. Roll number 7, are you there? He is leaving. Okay, he may have some problem. Okay, roll number 8. What roll number should I? 27. 24.
Yes, sir, 27. Sir, you are not audible.
Yeah, I am not audible.
Yes, sir. Now.
Okay. Now am I audible?
Yes, sir.
Yes, sir.
Now,
Have you understood?
Yes, sir.
Okay, very good. Roll number 31.
Yes, sir.
Have you understood?
Yes, sir.
Okay. So, anyone having any question? Otherwise, let's go ahead. So, let me delete everything which is there on the screen. And so this is the end of operations on the singly linked list, right? And now next is the operations on the circular linked linear list, circularly linked linear list, and this is a circularly linked linear list with a head node. We use the head node in the circular list, right? So here this head node never have the information part. So head node is just the pointer to the first node of the circular list, and the last node of the circular list is pointing back to this head node. So in this way, this is a managed, right, in this circular linked linear list. So let's go ahead. So here the operation on the circular linked list, the insertion at the head. So insertion at the head, this operation we want to do, and that we can do with this many steps. Here you may be thinking why this algorithm has just like written like this, because in a circular linked list, if you see, uh, 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 we can check, we can write the insertion in the insertion algorithm the same way we write the algorithm for insertion in the singly linked list, and that you can do. But uh, uh, this means you can use these steps in the insertion algorithm of the linearly linked list. So you already have linearly linked uh, uh, list, singly linked linear list, and this insertion algorithm you can modify and use these 4 steps to write the algorithm to insert the node at the head in the circular list. So let us see the steps. So how these steps work. So first of all, let me draw here one circular linked list, right? So let's say this is my circular linked list. Say there are 3 nodes, sorry, 2 nodes. One is the head. So in the head, as we know, no information is saved, right? And head node is just required. Instead of head, I just write H. So head node is just required to point to the first node in the circular linked list. So this is the first node and this is the second node, and the last node is pointing back to the head node. So this is my circular linked linear list, and now in that I want to follow this step. So first step is new equal to node. So I am getting one new node. Here you can check the availability, underflow, everything. same as the insertion in the singly linked linear list. So say this is the new node, right, and it is pointing to this, and information of new equal to y. So I want to add the node with information y, and the link of new equal to a link of head, right? So the link of new equal to the link of head, so that is it will be pointing to this, right? Are you getting this? And what next we want to do? Link of head is equal to new. So link of head is right now pointing to this node, so that I need to remove, and now link of this head node is pointing back to this new. So let me remove this, write this h below. I just took this at the bottom part of this head node, and now this head node, the link of head is equal to new. So the link of head is now getting updated by pointing to the new. So now you can see this, the head is pointing to this node is pointing to this is this, and this is again pointing to the head. So circular list is there. Or let me take this new node here so that you can better understand. So this was my circular list, right? And let me take node here only, that new node, so that you can understand. So this is new node, and the info of new is equal to y, and link of new is equal to link of head. So this would be pointing to this, and link of head is equal to new. So the link of head will be updated, and it will be pointing to a new node. Right. So now you can have a better diagram now. Here you can see the head, uh, the last node is still pointing to head. Head is pointing to the newly added node, and the new node is pointing to the uh, second node, and second node is pointing to third node, and third node is the last node, and it is pointing back to the head. So have you understood this? So this is the insertion at head. And may I go ahead? Any questions? Okay. So now this is the exercise from which the question may be asked in the exam. So here you can say the questions are: formulate a deletion algorithm for a circular list with a head node. Right. This in the here in the operations on circularly linked linear list, we have seen just insertion, and that algorithm is also not the complete algorithm. You can make it complete by looking at the insertion algorithm of the singly linked linear list, right? And So in this exercise, formulate algorithm to concatenate two circular lists, right? And design algorithm to split a circular list into two circular lists, right? And formulate insertion and deletion algorithms for Q which is represented by a circular list. Obtain an algorithm for the return of circular list to the availability area of the storage. And there are some string manipulation related exercise. You can go through it and you can practice for uh, exams. And let me go ahead now. Next topic is operations on the doubly linked linear list. So in the doubly linked linear list, the every node has two link parts instead of one link part. Right? So here you can see every node is pointing to the next node, and at the same time every node is also pointing to the previous node. Right? So this node is pointing to next node, this node is pointing to the next node, and so on. And at the same time every node is also pointing to the its predecessor, right? So here every node has two link parts, but the thing is the first node, there is no predecessor of first node, so the this link part will be null, and there is no the successor of the last node in the list, so the link part of the last node will be null, right? And this is a doubly linked representation of Q. That's why two pointers are maintained, F and R. Otherwise, you can maintain this doubly linked list, doubly linked linear list with just one pointer, right? First. But now let's see the operations on this doubly linked linear list. And in this first is the insertion operation, and let me check the time. Okay, we have time, it's a 35 minutes. So let's yeah. So the insertion in the doubly linked linear list, and this is the pseudo code for that. So first step is obtain a new node and set it fields. Check if the list is empty, and if it is empty, then insert the node in the list, update the left and right pointers to the list, and return. Because this is doubly linked list, we have now two pointers, left and right. So if the list is empty, the node is the first node to be inserted in the list, so that the left and right pointers would be set to null, right? And if the node is to be inserted at the front of the list, then insert the node and update the left pointer to the list and return. Or insert the node in the middle of the list and return. Okay, so let's go ahead. So this is the procedure, doubly insert, and here we are given a doubly linked linear list whose leftmost and rightmost node addresses are given by pointer L and R, right? And it is required to insert a node whose address is given by pointer new. The left and right links of a node are denoted by LPTR and RPTR. So every node has two pointers, and they are mentioned as LPTR and RPTR, and the whole W linked list is pointed by two pointer variables L and R, right? So L is for leftmost node and R is pointing to the rightmost node in the W linked list. Or in other words, you can say L is pointing to the first node and R is pointing to the last node. And the information field of a node is denoted by the info, and the name of the element the name of an element of the list is node, and so this is a like temporary variable, and the insertion is to be performed to the left of the specified node with its address given by the pointer variable m. See, this pointer variable m is the address of the node, and its address of node whose left side we want to add the new node, and this new node has the information part x. So have you got this description, everyone? So you have to keep in mind there is a say doubly linked list like this. Sorry, it is doubly linked list, so there will be two pointers, and here it is said that left and right are, so let me first of all make the first node and last node. The predecessor pointer of first node is null, or you can say LPTR, and RPTR of the last node is null, and L is pointing to the leftmost node, so, or you can say first node, and this R is pointing to the rightmost node, or you can say last node, and this it is required to insert a node whose address is given by the pointer variable new. So I have one more node, right, and it is pointed by the new. Okay, and the thing is the left and right links of the node are denoted by LPTR and RPTR. All this, every node has LPTR and RPTR, and we have to insert this node uh, at the left side of the node which is pointed by L. So now, first of all, let me draw the links here. So this is my doubly linked list, and here I have also been given the pointer m. So say m is, suppose, is pointing to the this node, or you can take any node. Say m is pointing to this node, and now the information of this new node is x, and we want that this new node is inserted, or so this new node is to be inserted at the left of the specified node, this m. So what you need to do, you need to update the links. So how you will update the links? So first of all, the next link of the new node should be the this links should be deleted, and the after this algorithm this should be pointing to this, and the predecessor of this is should be pointing to this, and uh, the next is pointing to this, and the predecessor is pointing to this. So think that so now this node is pointing to this node, and this node is the next part of this node is pointing to this. So this we want to do, right? With this algorithm, you have given the m pointer, and to the left of this m new node should be inserted. You are given the L and R, you are given the X, and you are also given a new node, and you have to do this, achieve this. Okay. So now let's go ahead to the algorithm. Let's see. Okay, so this is the algorithm, and I think we should. It's a 43 minutes we already have taken. So now I think we should understand this algorithm in next lecture. So any questions up to now? Okay then, let me close the PPT and let me stop sharing screen. Any questions? You can write down in
No,
chat.
sir.
No, sir.
Okay, thank you for being interactive. And now let me download the attendance sheet and let me stop recording.